the clearest night, far from any city, you might look up and feel as though you are seeing everything. The stars appear countless. The Milky Way stretches from one horizon to the other in a pale, luminous ribbon. If you are patient, you might notice a faint smudge of light, the Andromeda Galaxy, more than 2 million light-years away, reaching your eyes as a whisper of ancient photons. In that moment, the universe feels immense and visible, as if the sky is showing you all that exists. But it is not. What you see on even the finest night, every star, every galaxy, every nebula, every cluster of light scattered across the observable universe, accounts for roughly 5% of everything that is actually there. The remaining 95% is invisible. It produces no light. It casts no shadow. It cannot be touched, collected, or photographed. And yet without it, the universe you see would not exist. The galaxies would fly apart. The great cosmic web of matter that stretches across billions of light years would never have formed. The stars that burn so steadily above you would have no home. This is not poetry. This is one of the most carefully measured facts in modern science. And the largest share of that invisible universe belongs to something scientists call dark matter. The name itself is a quiet admission of ignorance. It is not called dark because it is dangerous or frightening. It is called dark because it does not interact with light in any way we can detect. It does not emit photons. It does not absorb them. It does not scatter, reflect, or block the light passing through it. In every experiment designed to catch light from the cosmos, dark matter is perfectly, completely silent, and yet its gravitational influence is everywhere. Every large galaxy in the universe appears to be embedded inside an enormous halo of dark matter, a vast invisible structure far larger than the visible galaxy itself. The stars, the gas, the dust, the spiral arms, all of it sits at the center of something much bigger, something we cannot see. The Milky Way, our own galaxy, is no exception. The disk of stars you see, stretching across the night sky, is surrounded by a dark matter halo that extends hundreds of thousands of light years in every direction. You are, at this very moment, drifting through it. The mystery of dark matter is not new. The first serious clues appeared nearly a century ago, when astronomers began measuring how galaxies move inside enormous clusters. The numbers did not make sense. The galaxies were moving too fast. There was not enough visible matter to hold them together. Something unseen had to be providing the extra gravitational pull. At first, this idea was met with skepticism. Perhaps the measurements were wrong. Perhaps the instruments were not precise enough. But as decades passed and observations became sharper, the evidence did not weaken. It grew stronger. Different teams using completely different methods kept arriving at the same conclusion. There is far more matter in the universe than we can see. Today, dark matter is not a fringe idea. It is one of the central pillars of modern cosmology. It is woven into the standard model of the universe, the framework that explains how everything from the cosmic microwave background to the largest galaxy clusters came to be. Without dark matter, that framework collapses. The equations do not balance. The structures do not form. The universe does not look the way it looks. And yet, despite nearly a century of evidence, no one has ever directly detected a dark matter particle. No laboratory on Earth has captured one. No detector has recorded its collision. No telescope has seen its glow. We know it is there because of what it does, not because of what it is. We see its fingerprints everywhere in the rotation of galaxies, in the bending of light around massive clusters, in the patterns of the oldest light in the universe, but the substance itself remains perfectly hidden. This is the documentary you are about to hear. Not a story of answers, but a story of one of the most important questions science has ever asked. How did we discover that most of the universe is invisible? What evidence convinced the scientific community that something vast and unknown surrounds every galaxy we can see. What do we think dark matter might be? And why, after all these years of searching, has it refused to reveal itself? There is no need to rush. The question has waited for nearly 100 years. It can wait a little longer tonight. Let the stars drift overhead, and let the story begin where all good science begins, with someone noticing that something did not add up. The year was 1933, and a Swiss-born astronomer named Fritz Zwicky was doing something that most of his colleagues considered tedious. He was studying galaxy clusters, enormous collections of galaxies bound together by gravity, drifting through space as a single vast system. The particular cluster that caught his attention was the Coma cluster, a rich gathering of over 1,000 galaxies located roughly 320 million light-years from Earth in the direction of the constellation Coma Berenices. Zwicky was not interested in the beauty of the cluster. He was interested in its physics. He wanted to understand how the galaxies within the Coma cluster moved, how fast they were traveling relative to one another, and whether that motion was consistent with the amount of matter he could see. It was a straightforward question, the kind of question that should have had a straightforward answer. He began by measuring the redshifts of individual galaxies within the cluster. Each galaxy emits light, and as it moves relative to an observer, that light shifts in wavelength. A galaxy moving away appears slightly redder. A galaxy approaching appears slightly bluer. By carefully measuring these shifts for many galaxies in the cluster, Zwicky could estimate their velocities, how quickly they were orbiting the center of mass of the entire system. Then he estimated the total mass of the cluster using the light it produced. Every star emits a predictable amount of energy based on its temperature and size. By measuring the total luminosity of the cluster, the combined light of all its galaxies, Zwicky could estimate roughly how many stars were present, and from that, how much mass the cluster should contain. This was a standard technique, well understood and widely trusted at the time. When he compared the two numbers, something was deeply wrong. The galaxies were moving far too quickly. Their velocities were so high that the visible matter in the cluster, all the stars in all the galaxies combined, could not possibly generate enough gravitational force to hold them together. If the only matter present was the matter that could be seen, the cluster should have flown apart long ago. The galaxies should have scattered into the void like sparks from a fire. But they had not scattered. The Coma cluster was stable. It was gravitationally bound. Something was holding it together, and that something was not visible. Zwicky calculated that the cluster would need roughly 400 times more mass than the visible matter could account for. 400 times. This was not a small discrepancy. This was not a rounding error or a modest uncertainty. The vast majority of the mass required to explain the cluster's behavior was simply missing, or rather, it was present but invisible. He called this unseen material dunkle materie, dark matter. It was a bold claim, and Zwicky was not a man known for timidity. He was brilliant, combative, and often difficult. His colleagues respected his intelligence, but frequently clashed with his personality. He had a habit of being right about things long before anyone was willing to agree with him, and dark matter would prove to be perhaps the most dramatic example of this pattern. The scientific community did not embrace his conclusion. The measurements were rough. The techniques were still being refined. The idea that most of the mass in a galaxy cluster could be invisible struck many astronomers as implausible, even absurd. There were simpler explanations that seemed more reasonable. Perhaps Zwicky had overestimated the velocities. Perhaps the cluster was not truly gravitationally bound. Perhaps there were forms of ordinary matter gas, dust, dim stars that simply had not been detected yet. The universe was full of things that were difficult to see. Proposing an entirely new form of invisible matter seemed, to many, like an unnecessary leap. And so the idea was quietly set aside, not disproven, not debated, not tested, simply ignored. For decades, dark matter remained an obscure footnote in the astronomical literature, a curiosity attached to a difficult personality. The broader scientific world moved on to other questions. New telescopes were built, new galaxies were catalogued, the universe expanded in the minds of astronomers as observations improved. But the mysteries Zwicky had uncovered lay dormant, waiting. It is worth pausing here to appreciate how common this pattern is in the history of science. An observation is made that does not fit existing understanding. The observer proposes a bold explanation. The community, understandably cautious, looks for simpler alternatives. And the original observation sits patiently, unresolved, until new evidence arrives that forces the question open again. This is not a failure of science. It is how science works. Caution protects against error. But sometimes, caution also delays recognition. There were a few researchers during this long quiet period who noticed similar problems. In the 1930s and 1940s, the astronomer Sinclair Smith studied the Virgo cluster and found a comparable discrepancy: galaxies moving faster than visible mass could explain. His conclusions echoed Zwicky's, but they too were largely overlooked. The tools were not precise enough, the theoretical framework was not ready, and the idea of invisible mass simply felt too strange to take seriously without overwhelming evidence. That evidence would eventually come, but it would not come from galaxy clusters. It would come from something much closer to home, from the way individual galaxies rotate, and it would come from an astronomer whose quiet determination and extraordinary precision would finally force the scientific world to confront what Zwicky had glimpsed decades earlier. But before that revolution arrived, it is important to understand what astronomers expected to find when they looked at galaxy rotation. The prediction was simple and elegant, rooted in the same physics that governs planets orbiting the Sun. In our solar system, the planets closest to the Sun move fastest. Mercury races around its orbit at nearly 50 kilometers per second. Earth moves at about 30. Jupiter, far from the Sun, lumbers along at roughly 13. Neptune, distant and cold, crawls at just over 5. The pattern is clear and mathematically precise. The farther an object is from the central mass, the slower it orbits. This is Keplerian rotation, named after Johannes Kepler, who described the laws of planetary motion in the early 17th century. Astronomers expected spiral galaxies to follow a similar pattern. The center of a galaxy contains the densest concentration of stars, the greatest concentration of visible mass. Stars and gas clouds farther from the center should, according to this logic, orbit more slowly. The rotation curve of a galaxy, a plot of orbital velocity versus distance from the center, should rise steeply near the core where mass is concentrated, and then decline smoothly at greater distances, falling off just as planetary velocities decline farther from the Sun. This expectation was clear, well-founded, and consistent with centuries of gravitational theory. When astronomers finally built instruments precise enough to measure galaxy rotation curves in detail, the result should have been a beautiful confirmation of Newtonian gravity applied on the grandest scale. What they found instead was one of the most important surprises in the history of science, and the person most responsible for revealing it was a young astronomer who had been told, more than once, that galaxy rotation was not a particularly interesting subject. Vera Rubin grew up in Washington, D.C., and from an early age she was fascinated by the night sky. As a girl, she would watch the stars move past her bedroom window, tracing their slow arcs across the glass. Captivated by the quiet precision of their motion, she knew early that she wanted to be an astronomer, though the path would not be simple. When she applied to graduate programs in the early 1950s, she encountered the reality that many prestigious astronomy departments did not admit women. Princeton's graduate program in astronomy would not accept female students until 1975. Rubin was undeterred. She completed her master's degree at Cornell and her doctorate at Georgetown, and she began a career that would, slowly and without fanfare, reshape our understanding of the universe. Her early work focused on the motion of galaxies, not the internal rotation of individual galaxies, but the way galaxies themselves move through space. Her doctoral dissertation suggested that galaxies were not distributed randomly, but showed signs of large-scale, coherent motion, a kind of cosmic flow. The idea was ahead of its time, and it was met with skepticism. But Rubin was patient. She continued working, continued measuring, continued trusting the data, even when the conclusions were unwelcome. By the late 1960s and into the 1970s, Rubin turned her attention to a question that seemed, on the surface, almost routine. She wanted to measure the rotation curves of spiral galaxies to determine how far stars and gas orbited at different distances from the galactic center. She was working at the Carnegie Institution of Washington alongside Kent Ford, an instrument maker who had built an extraordinarily sensitive spectrograph. This instrument could measure the Doppler shifts of light from individual regions within a galaxy, allowing Rubin and Ford to determine the orbital velocities of stars and gas clouds at various distances from the center with unprecedented precision. They began with the Andromeda galaxy, the nearest large spiral galaxy to the Milky Way. Andromeda was an ideal target, close enough to resolve individual regions, large enough to measure rotation at many different distances from the center, and well studied enough that any surprising result would be immediately significant. Rubin and Ford carefully measured the velocities of hydrogen gas clouds across the disk of Andromeda, plotting each measurement on a graph of velocity versus distance from the galactic center. The expectation, as established by decades of gravitational theory, was clear. Near the center, where most of the visible mass was concentrated, orbital velocities should be high. Farther out, where the density of stars and gas drops significantly, velocities should decline. The rotation curve should rise and then fall, following the same Keplerian patterns seen in the solar system. What they found was entirely different. Near the center of Andromeda, the rotation curve rose steeply, just as predicted. Stars and gas close to the core moved quickly, pulled by the dense concentration of mass. But as they moved their measurements outward past the bright central bulge, into the disk, and then to the faint outer edges of the galaxy, the velocities did not decline. They remained high. The rotation curve flattened out and stayed flat, stretching far beyond the visible edge of the galaxy at velocities that should have been impossible if the only mass present was the mass that could be seen. This was not a subtle effect. The outermost gas clouds in Andromeda were orbiting just as fast as material, much closer to the center. According to Newtonian gravity, this could only mean one thing. There was far more mass present than the visible stars and gas could account for, and this extra mass was not concentrated at the center. It was distributed in an enormous, extended structure surrounding the galaxy, a halo of invisible matter that stretched far beyond the luminous disk. Rubin and Ford moved on to other galaxies. They measured dozens of spiral galaxies over the following years, each one chosen to test whether the flat rotation curve of Andromeda was an anomaly or a pattern. Galaxy after galaxy, the result was the same. The rotation curves rose and then flattened. They did not decline. In every case, the outer regions of the galaxy were rotating faster than visible matter could explain. In every case, the gravitational influence of something unseen was required to make the observations consistent with physics. The consistency of the result was extraordinary. This was not a peculiarity of one galaxy or one type of galaxy. It appeared in large spirals and small ones, in galaxies seen face-on and edge-on, in galaxies near and far. Wherever astronomers looked with sufficient precision, the same flat rotation curves appeared. The pattern was universal. Rubin understood the significance of what she was seeing. In a careful, measured voice that would become her hallmark, she began presenting the results at conferences and in published papers. She did not overstate the conclusions. She did not claim to know what the invisible mass was. She simply showed the data clear, precise, repeatable, and let it speak. The rotation curves were flat. The visible mass was insufficient. Something else was there. The reaction was mixed. Some astronomers immediately recognized the importance of the work. Others resisted. The idea that galaxies were embedded in vast halos of invisible matter was difficult to accept. Not because the evidence was weak, but because the implications were so profound. If Rubin was right, then the luminous matter that astronomers had spent centuries studying, the stars, the gas, the dust, everything visible through every telescope ever built, was only a small fraction of the total mass in any given galaxy. The majority of the matter was dark. The universe was not what it appeared to be. Some researchers proposed alternative explanations. Perhaps the instruments were miscalibrated. Perhaps the hydrogen gas being measured did not accurately trace the gravitational potential. Perhaps there were large populations of dim, ordinary objects, faint stars, cold gas clouds, burnt-out stellar remnants lurking in the outer regions of galaxies, providing the missing mass without requiring any exotic new substance. These were reasonable objections, and each one was investigated carefully over the years that followed. One by one, the alternatives fell away. The instruments were tested and confirmed. Different tracers, not just hydrogen gas, but also carbon monoxide, planetary nebulae, and satellite galaxies, gave the same results. Searches for large populations of dim ordinary matter came up short. There simply were not enough faint stars, enough cold gas, enough stellar remnants to account for the enormous mass discrepancy. Whatever was producing the flat rotation curves was not made of the same material as everything else in the visible universe. Rubin continued her work with characteristic patience and precision. She and Ford eventually published rotation curves for more than 60 galaxies, building a dataset so comprehensive that the flat rotation curve became one of the most firmly established observational facts in extragalactic astronomy. The evidence was no longer a curiosity, it was a pillar. What made Rubin's contribution so powerful was not just the data itself, but the way she gathered and presented it. She was meticulous, she was cautious, she was honest about uncertainties. The read, she let the measurements accumulate until the weight of evidence became impossible to dismiss. She did not seek controversy, she sought understanding. And in doing so, she provided the single most compelling body of evidence that the universe is filled with matter we cannot see. By the early 1980s, the scientific consensus had shifted. The flat rotation curves measured by Rubin, Ford, and a growing number of independent teams around the world had become one of the strongest pillars supporting the existence of dark matter. Fritz Zwicky's forgotten observation from 1933 was vindicated. The missing mass he had glimpsed in the Coma cluster was not an error, it was real, and it was everywhere. But the rotation curves were not the only evidence. Even as Rubin was measuring how galaxies spin, another entirely independent line of evidence was emerging, one that did not involve galaxies at all, but the bending of light itself. Einstein had predicted decades earlier that massive objects could curve the fabric of space-time and deflect light passing nearby. If dark matter truly surrounded galaxies and galaxy clusters in enormous invisible halos, then its gravitational influence should be visible, in the way light from distant sources was bent and distorted as it passed through these hidden structures. Astronomers were about to discover that the universe had been leaving clues in the shape of light all along. Albert Einstein published his general theory of relativity in 1915, and among its many predictions was one that must have seemed almost fantastical at the time. He proposed that mass does not simply pull on other mass through some invisible force acting across empty space. Instead, mass warps the fabric of space-time itself. A massive object, a star, a galaxy, an entire cluster of galaxies, creates a curvature in the geometry of the space surrounding it, and everything moving through that curved space follows the curvature. Light, despite having no mass of its own, is no exception. A beam of light passing near a massive object will follow the curved space-time and bend, just as a marble rolling across a stretched rubber sheet curves toward a heavy ball sitting at the center. This effect is called gravitational lensing, because the massive object acts like a lens, bending and focusing light from sources behind it, distorting their appearance, sometimes magnifying them, sometimes stretching them into arcs and rings. Einstein himself doubted that the effect would ever be practically observable for objects beyond the sun. The deflection angles were tiny, the alignment required was improbable, and the instruments of his era were far too crude to detect such subtle distortions in the images of distant galaxies. He underestimated the future. By the second half of the 20th century, telescopes had become powerful enough to observe gravitational lensing on cosmic scales. And when astronomers turned those telescopes toward massive galaxy clusters, the largest gravitationally bound structures in the universe, they found something that confirmed, in an entirely independent way, what Vera Rubin had been measuring in the rotation curves of spiral galaxies. The first strong gravitational lenses were discovered in the late 1970s and 1980s. Astronomers noticed that certain distant quasars, extremely luminous objects powered by supermassive black holes at the centers of distant galaxies, appeared to have multiple images in the sky. 2, 3, sometimes 4 separate images of the same quasar, arranged symmetrically around a foreground galaxy or galaxy cluster. The explanation was gravitational lensing. The massive foreground object was bending the light from the background quasar along multiple paths, each path producing a separate image from the observer's perspective. It was Einstein's prediction brought to life, and it was beautiful. But the beauty carried a problem. When astronomers calculated how much mass the foreground object would need in order to produce the observed lensing effect, the degree of bending, the separation of the images, the precise geometry of the arcs, the answer was always the same. The visible matter was not enough. The stars and gas in the foreground galaxy or cluster could not account for the gravitational bending being observed. There had to be more mass present. Mass that could not be seen. Mass that was contributing to the curvature of space-time without producing any detectable light. This was dark matter, revealing itself not through the motion of stars or galaxies, but through the shape of space itself. As telescopes improved, astronomers began to observe a more subtle form of gravitational lensing called weak lensing. Strong lensing produces dramatic arcs and multiple images, but it requires a nearly perfect alignment between the background source, the foreground lens, and the observer. Weak lensing is far more common. It occurs whenever light from distant galaxies passes through the gravitational field of intervening mass, not enough to produce arcs or multiple images, but enough to slightly distort the shapes of the background galaxies. Each individual distortion is tiny, almost imperceptible, but when astronomers measure the shapes of thousands or millions of background galaxies across a wide field of view, a statistical pattern emerges. The distortions are not random, they are coherent, aligned in a way that traces the distribution of mass in the foreground, including mass that cannot be seen. Weak lensing became one of the most powerful tools in modern cosmology. It allowed astronomers to map the distribution of total mass both visible and dark across enormous volumes of the universe. The maps that emerged were striking. They showed that dark matter is not scattered randomly through space. It is organized into vast structures, filaments, sheets, and halos, forming an enormous cosmic web that stretches across billions of light years. The visible galaxies sit within this web like dewdrops on a spider's silk, tracing the underlying dark matter scaffolding, but representing only a small fraction of the total mass. One of the most celebrated observations in the history of dark matter research came from a single extraordinary object, the Bullet Cluster. Located roughly 3.7 billion light-years from Earth, the Bullet Cluster is actually two galaxy clusters that collided, or more precisely, passed through each other at enormous speed. This collision created a natural laboratory for separating dark matter from ordinary matter, and the results it produced are among the most compelling pieces of evidence that dark matter is real and distinct from ordinary matter. When two galaxy clusters collide, different components behave differently. The individual galaxies in each cluster, separated by vast distances, pass through each other largely unaffected, like two swarms of bees flying through one another. The hot intergalactic gas, however, does not pass through so easily. Gas from one cluster collides with gas from the other, creating enormous shock waves and heating to extreme temperatures. This hot gas can be observed directly in X-ray wavelengths, and in the Bullet Cluster, X-ray telescopes showed a clear picture of where the ordinary matter ended up after the collision concentrated in the center, between the two separating clusters slowed by the impact. But when astronomers used gravitational lensing to map the total mass of the system, the mass responsible for bending the light of background galaxies, they found something remarkable. The majority of the mass was not where the hot gas was. It had passed straight through the collision, continuing outward with the galaxies on either side. The gravitational mass and the ordinary matter had separated. The dark matter, whatever it is, had continued moving as though the collision had not happened, because it does not interact with ordinary matter or with itself through any force other than gravity. This separation was exactly what would be expected. If dark matter is a substance that interacts gravitationally but does not collide, scatter, or experience friction the way ordinary matter does, it was a direct, visual demonstration that the missing mass is not simply ordinary matter hiding in some undetectable form. It is something fundamentally different, something that passes through both itself and ordinary matter, like a ghost through a wall, responding only to the curvature of space-time. The Bullet Cluster was not an isolated case. Subsequent observations found similar separations in other merging clusters, each one reinforcing the conclusion. The dark matter component and the ordinary matter component could be pulled apart by collisions, and when they were, the gravitational lensing always followed the dark matter, not the gas. The mass was where the invisible substance was, not where the visible substance was. Gravitational lensing also provided something that rotation curves alone could not, a way to measure the total amount of dark matter in the universe, not just in individual galaxies. By analyzing the weak lensing signal across enormous surveys of the sky, millions of galaxies, thousands of square degrees, cosmologists could estimate the total density of matter in the universe. The results consistently showed that ordinary matter, the atoms and molecules that make up stars, planets, gas clouds, and human beings, accounts for roughly 5% of the total energy content of the universe. Dark matter accounts for roughly 27%. The remaining 68% belongs to something even more mysterious, dark energy. But that is a question for another night. The gravitational lensing evidence accomplished something essential. For the dark matter hypothesis, it confirmed the existence of invisible mass using a completely independent method. rotation curves measured how galaxies move. Gravitational lensing measured how light bends. Both pointed to the same conclusion. Both required the same invisible substance, and both were consistent with general relativity, the most precisely tested theory of gravity ever devised. There is a quiet elegance to this convergence. Two entirely different physical phenomena, the orbits of stars and the bending of light, governed by the same underlying theory, both demanding the presence of the same unseen mass. The universe was not offering a single clue. It was offering a pattern, a consistent, repeating, unavoidable signal that something vast and invisible was shaping reality at every scale, from the rotation of individual spiral galaxies to the collision of enormous galaxy clusters, from the subtle distortion of distant galaxy shapes to the grand architecture of the cosmic web. Dark matter left its signature everywhere astronomers learned to look. But even this was not the end of the evidence. While Vera Rubin measured galactic rotation and gravitational lensing revealed the bending of light, another signal was emerging from a completely different source, not from the universe as it exists today, but from the universe as it existed nearly 14 billion years ago. The oldest light in existence was carrying its own message about dark matter, encoded in patterns so faint and precise that decoding them would require sending instruments beyond the atmosphere of the Earth itself. Roughly 380,000 years after the Big Bang, something remarkable happened. The universe, which had been a blinding fog of plasma since its birth, finally cooled enough for atoms to form. Protons captured electrons, hydrogen atoms assembled for the first time. And with that transition, the universe became transparent, light, which had been trapped in the plasma, scattered endlessly by free electrons, unable to travel any meaningful distance, was suddenly released. It streamed outward in every direction, filling the cosmos with a bath of photons that has been traveling ever since. That light is still here. It has been stretched by the expansion of the universe from its original visible glow into faint microwave radiation, but it is still detectable. It fills every cubic centimeter of space. It comes from every direction equally. It is the oldest light in existence, and it carries within it a portrait of the universe as it appeared when it was less than 500,000 years old. Scientists call it the cosmic microwave background, and it has become one of the most important sources of information in all of cosmology. When the cosmic microwave background was first detected in 1965 by Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey, it appeared almost perfectly uniform, no matter where they pointed their antenna, north, south, east, west, toward the plane of the Milky Way, or away from it, the signal was the same. A faint hiss of microwave radiation corresponding to a temperature of roughly 2.7 degrees above absolute zero, arriving from every part of the sky with astonishing consistency. This uniformity was itself a profound discovery. It confirmed that the early universe was remarkably smooth, nearly identical in temperature and density in every direction, exactly as the Big Bang theory predicted. But the universe today is not smooth. Today, matter is gathered into galaxies, galaxy clusters, filaments, and vast empty voids. Structure exists everywhere. If the early universe had been perfectly uniform, with no variations in density whatsoever, there would have been no seeds for this structure to grow from. Gravity would have had nothing to work with. The universe would have expanded into a featureless, starless emptiness. So the cosmic microwave background could not be perfectly uniform. There had to be tiny variations, slight differences in temperature from one patch of sky to another, corresponding to slight differences in the density of matter in the early universe. Regions that were slightly denser than average would eventually attract more matter through gravity, growing over billions of years into the galaxies and clusters we see today. Regions that were slightly less dense would become the great cosmic voids The seeds of all structure had to be encoded in the cosmic microwave background, written in temperature differences, so small that detecting them would push the limits of human technology. The first spacecraft to map these variations was the Cosmic Background Explorer, known as COBE, launched by NASA in 1989. COBE confirmed that the cosmic microwave background was not perfectly uniform. It detected temperature fluctuations on the order of 1 part in 100,000, extraordinarily faint ripples in the oldest light, variations so subtle that they had eluded every previous instrument. The announcement of these results in 1992 was met with astonishment. George Smoot, the lead scientist on the project, described the experience of seeing those faint patterns as looking at the face of God. The ripples were the seeds from which the entire observable universe would grow. But COBE's resolution was limited. It could see that fluctuations existed, but it could not map their fine structure. To understand what those fluctuations meant to decode the information they carried about the composition and physics of the early universe, astronomers needed sharper maps. That next step came with the Wilkinson Microwave Anisotropy Probe, known as WMAP, launched in 2001, and later with the Planck satellite, launched by the European Space Agency in 2009. Each generation of instrument produced maps of increasing precision, revealing finer and finer details in the pattern of temperature fluctuations across the sky. What emerged from these maps was extraordinary. The fluctuations were not random noise. They had a specific statistical pattern, a characteristic distribution of hot and cold spots at different angular scales. When cosmologists analyzed this pattern, decomposing it into its component frequencies, much as a musician might decompose a complex sound into individual notes, they found a series of peaks and troughs. These peaks corresponded to sound waves that had traveled through the plasma of the early universe before the moment of transparency, compressing and expanding the fluid of matter and radiation in a regular, predictable pattern. These are called acoustic oscillations, and they are among the most powerful tools in cosmology. The precise positions, heights, and spacing of the acoustic peaks encode detailed information about the composition of the universe. They reveal how much ordinary matter was present, how much radiation, how much dark matter, and how much dark energy. They constrain the geometry of the universe, the rate of expansion, the age of the cosmos, and the initial conditions that set everything in motion. And when cosmologists fit theoretical models to the observed acoustic peaks, one conclusion was inescapable. The pattern could not be reproduced using ordinary matter alone. The heights and positions of the peaks required a substantial component of matter that does not interact with light, matter that contributes gravitational influence, but does not participate in the acoustic oscillations of the plasma. In other words, the peaks required dark matter. The reason lies in the physics of the oscillations themselves. In the early universe, ordinary matter and radiation were tightly coupled. Photons and baryons, protons and neutrons formed a single fluid, and pressure waves traveled through this fluid like sound through air. Regions of higher density were compressed by gravity, then pushed back outward by radiation pressure, creating oscillations. These oscillations left their imprint on the cosmic microwave background at the moment of transparency, frozen in place when photons decoupled from matter and began their long journey across the universe. Dark matter, however, does not interact with photons. It does not feel radiation pressure. It does not participate in the acoustic oscillations. Instead, it simply responds to gravity. While the ordinary matter was oscillating, compressing, and expanding under the competing influences of gravity and radiation pressure, dark matter was quietly accumulating in the denser regions, deepening the gravitational potential wells without being pushed back by pressure. This difference between the behavior of ordinary matter and dark matter leaves a distinctive signature in the acoustic peaks, the relative heights of the odd and even peaks, the overall shape of the power spectrum, the damping of fluctuations at small scales. All of these depend sensitively on the ratio of dark matter to ordinary matter. The Planck satellite measured this ratio with extraordinary precision. Its final results, published after years of careful analysis, indicated that ordinary matter makes up approximately 5% of the total energy content of the universe, while dark matter accounts for roughly 27%. These numbers were consistent with earlier measurements from WMAP, from gravitational lensing surveys, from galaxy cluster analyses, and from the dynamics of galaxy rotation curves. Every independent method was converging on the same answer. The universe contains about 5 times more dark matter than ordinary matter. This convergence is worth pausing to appreciate. The cosmic microwave background carries information from the universe. At an age of 380,000 years, galaxy rotation curves measure the universe as it exists today, billions of years later. Gravitational lensing probes the distribution of mass at intermediate distances. The bullet cluster captures a specific event in a specific location. These are completely independent observations, made with different instruments, using different physical principles, examining different epochs and different scales. And yet, they all agree. They all require the same invisible substance, in the same proportion, distributed in the same way. The consistency of this evidence is one of the most compelling arguments in all of modern science. There is something deeply humbling about the cosmic background. This light has been traveling for nearly 14 billion years. It left the surface of last scattering before any star had formed, before any galaxy existed, before any planet or moon or ocean or living thing had come into being. It has crossed the entire observable universe to reach our instruments, carrying with it a message from the infancy of everything. And encoded in that message, written in temperature differences smaller than a fraction of a degree, is the unmistakable signature of dark matter present from the very beginning, shaping the universe, long before there was anyone to wonder what it was. The evidence from the cosmic microwave background did more than confirm the existence of dark matter. It constrained its properties. It told cosmologists that dark matter must be cold, meaning it moves slowly compared to the speed of light, because only cold dark matter produces the correct pattern of structure formation. Hot dark matter, made of fast-moving particles like neutrinos, would smooth out the small-scale density fluctuations and prevent the formation of the galaxies and clusters observed today. The universe we see is a universe sculpted by cold, slow-moving, gravitationally dominant, invisible matter, and the acoustic peaks of the cosmic microwave background are among the clearest windows into that reality. By the early 21st century, the evidence for dark matter had become overwhelming, not because of any single observation, but because of the extraordinary agreement between entirely independent lines of evidence. Galactic rotation curves demanded it. Gravitational lensing confirmed it. The cosmic microwave background encoded it. Galaxy cluster dynamics required it. The large-scale structure of the universe depended on it. Every probe, every method, every instrument pointed in the same direction. The question was no longer whether dark matter exists. The question had become something far more difficult and far more exciting. What is it? The simplest hope was that dark matter would turn out to be something familiar. Perhaps it was ordinary matter, the same protons, neutrons, and electrons that make up everything we can touch and see, just hidden in forms too faint or too cold to detect easily. Astronomers had a name for these hypothetical objects. They called them MACHOs, massive astrophysical compact halo objects. The category included brown dwarfs, failed stars too small to ignite hydrogen fusion, drifting through galactic halos in enormous numbers. It included old white dwarfs that had cooled beyond detection, neutron stars that no longer pulsed, black holes of modest size scattered through the darkness. Any of these could, in principle, contribute mass to a galaxy without producing detectable light. The idea was appealing because it required no new physics. If dark matter were simply ordinary matter in dim packaging, the mystery would dissolve into a problem of detection rather than a crisis of fundamental understanding. The universe would still be made of familiar ingredients, just arranged in ways that had escaped observation. To test this hypothesis, astronomers designed an elegant experiment based on gravitational microlensing. If millions of compact dark objects truly populated the halo of the Milky Way, then occasionally one of them should pass between Earth and a distant background star, a star in the Large Magellanic Cloud, for instance. A satellite galaxy visible from the southern hemisphere. When this alignment occurred, the gravity of the compact object would briefly bend and focus the light of the background star, causing it to brighten temporarily in a smooth, symmetric, achromatic curve. The brightening would last days or weeks, depending on the mass of the lensing object, and it would look nothing like the intrinsic variability of ordinary stars. It would be a gravitational signature, unmistakable and clean. Two major surveys were launched to search for these events: the Macho Project and the Eros Project, both monitoring millions of stars in the Magellanic Clouds night after night, watching for the telltale brightening that would reveal a dark, compact object passing through the foreground. The surveys ran for years, accumulating vast datasets. They found some microlensing events, but not nearly enough. The number of detections was far below what would be expected if Machos accounted for the majority of the Milky Way's dark matter halo. Brown dwarfs, white dwarfs, neutron stars, and stellar mass black holes existed in the halo, certainly, but their combined mass fell dramatically short of the total required. The surveys concluded that Machos could account for, at most, a small fraction of the dark matter. The vast majority of the missing mass was not made of ordinary baryonic matter in any form. This conclusion was independently supported by an entirely different line of evidence: Big Bang nucleosynthesis. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur on a cosmic scale. Protons and neutrons collided and combined, forming the lightest elements: hydrogen, helium, and tiny traces of lithium and deuterium. The precise abundances of these elements depend sensitively on the total density of ordinary matter in the early universe. By measuring the cosmic ratios of hydrogen to deuterium, helium-3 to helium-4, and lithium-7, cosmologists could calculate exactly how much ordinary baryonic matter the universe contains. The answer was consistent and unambiguous. Ordinary matter accounts for roughly 5% of the total energy content of the universe, the same figure derived independently from the cosmic microwave background. If dark matter were made of baryons, the element ratios produced in the Big Bang would look completely different. The deuterium abundance alone rules out a baryonic explanation for dark matter. Whatever dark matter is, it is not made of protons, neutrons, or any combination of the particles that constitute ordinary atoms. This was the moment the question shifted from astronomy to particle physics. If dark matter is not ordinary matter, then it must be composed of some particle or family of particles not included in the standard model of particle physics, or at least not in any configuration that interacts with light or participates in nuclear reactions. It must be something new. The leading candidate for decades has been a class of hypothetical particles called WIMPs weakly, interacting massive particles. The name describes their expected properties. They would have mass, contributing gravitational influence. They would interact through the weak nuclear force, one of the four fundamental forces of nature, but not through electromagnetism. This means they would not emit, absorb, or reflect light. They would pass through ordinary matter, almost unimpeded, interacting so rarely that detecting even a single collision would require extraordinary sensitivity. WIMPs emerged as the favored candidate, partly because of a remarkable numerical coincidence known as the WIMP miracle. If a particle with a mass roughly between 10 and 1,000 times the mass of a proton were produced in the hot early universe and interacted with the strength of the weak nuclear force, then, as the universe cooled and expanded, these particles would naturally freeze out at a density that matches the observed density of dark matter today. The calculation was not designed to produce this result. It emerged naturally from well-understood thermal physics, and the fact that it gave the right answer without any fine-tuning suggested that WIMPs might be real. Theoretical physics offered specific WIMP candidates. Supersymmetry, a theoretical framework that proposes a heavier partner particle for every known particle in the Standard Model, predicts the existence of a lightest supersymmetric particle called the neutralino. If the neutralino is stable, meaning it does not decay into lighter particles, it would have exactly the properties expected of a WIMP. It would be massive, electrically neutral, and weakly interacting. It would have been produced abundantly in the early universe, and it would persist today as a cold, invisible relic, filling the halos of galaxies and shaping the cosmic web. Other candidates exist beyond WIMPs. Actions, originally proposed to solve a different problem in particle physics, the strong CP problem, related to why the strong nuclear force treats matter and antimatter symmetrically, are extremely light particles that could have been produced in enormous quantities in the early universe. If they exist, axions would be astonishingly abundant, but almost impossible to detect, interacting with ordinary matter even more weakly than neutrinos. Their collective gravitational influence, however, could be enormous. Sterile neutrinos represent another possibility. Ordinary neutrinos, the ghostly particles produced in nuclear reactions, capable of passing through light years of solid lead without interacting, are part of the Standard Model, but they are far too light and too fast to account for dark matter. A hypothetical heavier cousin, the sterile neutrino, would interact even more weakly than ordinary neutrinos, coupling to the rest of the universe only through gravity and perhaps a faint mixing with its lighter relatives. If sterile neutrinos exist at the right mass, they could constitute some or all of the dark matter. More exotic possibilities have been proposed as well. Primordial black holes. Black holes, formed not from the collapse of dying stars, but from density fluctuations in the earliest moments of the universe, could contribute to the dark matter budget. These objects would be invisible, massive, and gravitationally influential. Recent interest in primordial black holes has been revived by the detection of gravitational waves from merging black holes, some of which had masses that were difficult to explain through conventional stellar evolution. However, various observational constraints have limited the mass ranges in which primordial black holes could account for all of dark matter, and most cosmologists consider them a partial contributor at best. The landscape of dark matter candidates is broad, and the list continues to expand as theorists explore new possibilities. Self-interacting dark matter, fuzzy dark matter, composed of ultralight particles with wave-like behavior on galactic scales, dark photons, mirror matter, dark sectors with their own internal forces and structures. The theoretical imagination has been fertile, but imagination alone does not solve the problem. What matters is evidence, and despite decades of searching, no experiment has yet confirmed the identity of the dark matter particle. This absence of detection is itself an important piece of information. It tells scientists what dark matter is not. It constrains the possible mass ranges, interaction strengths, and production mechanisms. Every null result from every experiment narrows the space of possibilities, guiding theorists toward the remaining corners where dark matter might still be hiding. The search is not failing. It is focusing. The challenge of identifying dark matter is fundamentally different from the challenge of proving its existence. Existence has been demonstrated through multiple independent gravitational observations. Identity requires catching the particle, directly seeing it interact with ordinary matter in a laboratory, or producing it in a particle accelerator, or detecting its annihilation or decay products in space. Each of these approaches has been pursued with extraordinary ingenuity and resources, and each has revealed, so far, only silence. That silence is not discouraging to the physicists who have dedicated their careers to this search. They understand that dark matter, by definition, interacts extraordinarily weakly with the world we can see. Finding it was always going to be one of the hardest things science has ever attempted. The experiments are not designed for quick result. They are designed for patience, for precision, and for the slow accumulation of data over years and decades. The scientists who build these detectors know that the answer might not come during their careers. They build them anyway because the question is too important to leave unanswered. Deep beneath the surface of the Earth, in places where no sunlight has ever reached, some of the most sensitive instruments ever built are waiting in perfect silence. They are not telescopes. They are not cameras. They are not designed to capture light of any kind. They are designed to detect the faintest possible interaction between a dark matter particle and an ordinary atom, a collision so gentle, so rare, and so subtle that finding it requires eliminating virtually every other source of disturbance that exists in the physical world. These are the direct detection experiments, and they represent one of the most ambitious undertakings in the history of experimental physics. The logic behind them is simple. If the Milky Way is embedded in an enormous halo of dark matter, then dark matter particles must be streaming through the solar system at all times. The Earth, as it orbits the Sun, moves through this invisible halo like a ship, cutting through a calm sea. Every second, billions of dark matter particles may be passing through every square meter of the Earth's surface. They pass through rock, through water, through metal, through human bodies, without leaving any trace. But if dark matter interacts through the weak nuclear force, as WIMPs are predicted to, then, very occasionally, perhaps a few times per year in a large enough detector, perhaps less, a single dark matter particle might collide with the nucleus of an ordinary atom and transfer a tiny amount of energy. That energy would appear as a faint signal, a small vibration, a flicker of heat, a brief flash of light. Detecting that signal is the challenge. The energy deposited by such a collision would be extraordinarily small, far smaller than the energy released by natural radioactive decay, far smaller than the disturbance caused by a single cosmic ray passing through the detector. The experiment must be sensitive enough to detect this faint whisper while remaining deaf to the constant roar of background noise from every other source. This is why the detectors are built underground. The surface of the Earth is bathed in cosmic rays, high-energy particles from space, that continuously bombard the atmosphere and penetrate into the ground. At the surface, these particles would overwhelm any dark matter signal. But deep underground, hundreds or thousands of meters of solid rock act as a natural shield, absorbing the cosmic rays and reducing their flux by factors of millions. The deeper the laboratory, the quieter the environment. Some of the world's deepest underground laboratories have been constructed specifically for this purpose. The Laboratory Nazionale del Gran Sasso in central Italy sits beneath nearly 400 meters of rock in the Apennine Mountains. The Sanford Underground Research Facility in South Dakota occupies a former gold mine. with detectors positioned nearly 1,500 meters below the surface. Snow Lab in Sudbury, Canada, operates 2 kilometers underground in a working nickel mine. Each of these facilities provides an environment of extraordinary quiet, a place where the noise of the cosmos is reduced to almost nothing, and the only signals that remain are the ones scientists are trying to find. But going underground is only the beginning. Even deep beneath the Earth, natural radioactivity is everywhere. The rock itself contains trace amounts of uranium, thorium, potassium-40, and other radioactive isotopes that decay continuously, emitting particles that can mimic a dark matter signal. The materials used to build the detector, the metal housing, the cables, the electronics, the support structures also contain trace radioactive contamination. Even the air in the laboratory carries radon, a radioactive gas that seeps from surrounding rock and whose decay products can deposit energy in the detector. Eliminating these backgrounds has driven direct detection experiments to extraordinary levels of material purity. The xenon used in liquid xenon detectors is purified to remove krypton-85, a radioactive isotope produced by nuclear reactors and weapons tests, to levels of parts per quadrillion, a purity that exceeds almost any other substance on Earth. The titanium used in detector vessels is screened for radioactive contamination with such precision that individual atoms of unwanted isotopes can be counted. Every component that enters the detector is tested, selected, and certified to meet radiological standards that would seem excessive in any other context, but are merely necessary here. The most prominent direct detection technology in recent years has been the dual-phase liquid xenon time projection chamber. These detectors use large volumes of ultra-pure liquid xenon as both the target and the detection medium. When a particle interacts with a xenon nucleus, it produces two signals: a prompt flash of scintillation light and a delayed charge signal from ionization. Electrons, drifted upward by an electric field into a thin layer of gaseous xenon above the liquid surface, where they produce a second flash by measuring the timing, position, and ratio of these two signals. Scientists can determine the type of interaction, its energy, and its location within the detector. Crucially, they can distinguish between nuclear recoils, the kind of signal expected from a dark matter collision, and electron recoils caused by background radiation. The Xenon experiment, located at Gran Sasso, has been a leader in this approach. Its successive generations, Xenon 10, Xen 1, T, and the current Exonant, have each increased the target mass and decreased the background levels, pushing sensitivity to ever lower interaction cross-sections. The Lux Zeppelin experiment, known as LZ, operating at the Sanford Underground Research Facility, uses a similar technology with nearly 10 tons of liquid xenon, making it one of the largest dark matter detectors ever built. Panda X, located in the China Jinping Underground Laboratory, the deepest underground laboratory in the world, beneath more than 400 meters of marble, represents another major effort in the same technological family. These experiments have achieved sensitivities that would have seemed impossible a generation ago. They can detect energy deposits equivalent to a few electrons being knocked free from their atoms. They can localize interactions within the detector volume to within millimeters. They can operate stably for months or years, accumulating exposure time while maintaining backgrounds at levels approaching zero events in the signal region. And yet, none of them have detected dark matter. The null results from these experiments are published with the same scientific rigor as any positive detection would be. Each null result sets a new upper limit on the interaction cross-section between dark matter particles and ordinary nuclei, a number that describes how likely a collision is per unit of target mass and time. With each new generation of detector, these limits have dropped by orders of magnitude. The space in which WIMPs can hide has been shrinking steadily, year by year, as the instruments grow larger and quieter and more sensitive. This progressive narrowing has had a profound effect on the theoretical landscape. Many of the simplest WIMP models, the versions of supersymmetry that most naturally predicted dark matter particles at accessible interaction strengths, have been excluded by direct detection results. The WIMP miracle, once considered a compelling hint, now appears less miraculous. The parameter space that remains viable is increasingly constrained, requiring more complex models or more finely tuned assumptions. But the search has not been limited to underground detectors. A parallel effort has been underway at the largest particle accelerators in the world, most notably the Large Hadron Collider at CERN. Straddling the border between France and Switzerland, the strategy at colliders is fundamentally different from direct detection. Rather than waiting for dark matter to come to the detector, collider experiments attempt to create dark matter by smashing ordinary particles together at extreme energies. If dark matter particles can interact with ordinary matter through the weak force, then the reverse should also be true. Collisions between ordinary particles at sufficiently high energies should occasionally produce dark matter particles. These particles would escape the detector unseen, carrying away energy and momentum. Their presence would be inferred not from what is observed, but from what is missing, an imbalance in the total energy and momentum of the collision products. Physicists call this missing transverse energy, and it is one of the primary signatures searched for in collider dark matter experiments. The ATLAS and CMS experiments at the Large Hadron Collider have conducted extensive searches for events with large missing transverse energy, looking for signs that dark matter particles were produced and escaped undetected. They have searched for the signatures predicted by supersymmetry cascades of heavier partner particles decaying down to the lightest supersymmetric particle, which would be the dark matter candidate. They have searched for simpler models in which dark matter is produced directly through a mediator particle. They have explored dozens of theoretical scenarios, each with its own predicted signatures and backgrounds. So far, none of these searches have found dark matter. The Large Hadron Collider has discovered the Higgs bosons, confirming the mechanism by which particles acquire mass, but it has not found supersymmetric particles, extra dimensions, or any of the new physics that many theorists expected. This absence has not disproven the existence of dark matter. Collider searches are sensitive only to certain mass ranges and interaction types, but it has added to the growing tension between theoretical expectations and experimental reality. A third approach to detection looks not downward into underground laboratories or inward at particle collisions, but upward into the sky. If dark matter particles can annihilate when they encounter each other, two wee WIMPs meeting in a dense region and converting their mass into ordinary particles and radiation, or if they can decay over cosmological timescales, then the products of these processes might be detectable as excess gamma rays, neutrinos, positrons, or antiprotons coming from regions of high dark matter density, such as the center of the Milky Way, nearby dwarf galaxies, or the Sun itself. Space-based instruments like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer on the International Space Station have searched for these indirect signals with remarkable sensitivity. Fermi has mapped the gamma ray sky with unprecedented resolution, searching for excess emission from the galactic center and from dwarf spheroidal galaxies, small, dark matter-dominated systems that produce very little astrophysical background. The Alpha Magnetic Spectrometer has measured cosmic ray positrons with extraordinary precision, looking for an excess above what conventional astrophysical sources would produce. Some intriguing hints have appeared. An excess of gamma rays from the galactic center, detected by Fermi, sparked intense debate about whether it might be the first indirect signal of dark matter annihilation. But alternative explanations, populations of millisecond pulsars, cosmic ray interactions with interstellar gas, remain viable. The positron excess, measured by the alpha magnetic spectrometer, could be consistent with dark matter annihilation. But it could also be explained by nearby pulsars. In each case, the signal is ambiguous, the backgrounds are complex, and the definitive identification of a dark matter signature has remained elusive. The combined result of direct detection, collider searches, and indirect detection is a picture of remarkable effort and remarkable silence. Thousands of physicists across dozens of countries have built some of the most extraordinary instruments in human history, pushed the boundaries of material science, electronics, computing, and statistical analysis, and listened with exquisite sensitivity for a signal from the invisible universe. They have not found it yet, but the silence itself has taught us enormously. It has ruled out entire families of theoretical models. It has constrained the properties of dark matter far more tightly than observation alone could. It has forced theorists to consider alternatives they might otherwise have ignored, and it has demonstrated that whatever dark matter is, it is remarkably good at interacting with the visible universe so faintly that even our most sensitive instruments have not yet been able to catch it in the act. The search continues. New detectors are being designed and built, larger and more sensitive than anything that has come before. New theoretical ideas are being explored, expanding the range of possibilities beyond the traditional WIMP paradigm. And new observational techniques, gravitational wave astronomy, precision cosmology, 21-centimeter hydrogen mapping promise to open entirely new windows onto the dark universe. The silence is not an ending, it is a challenge, and the scientists who pursue dark matter understand that some of the most important discoveries in history were preceded by long periods of patient, careful, apparently fruitless searching. There is another way to see dark matter, though it requires looking not at individual galaxies or clusters, but at the universe as a whole. If you could somehow rise above the cosmos and observe the distribution of all matter across billions of light years, you would not see a uniform scattering of galaxies. You would see a web, an enormous, intricate, three-dimensional network of filaments and nodes, with galaxies strung along the filaments like beads on threads of silk, and vast empty voids stretching between them, regions of space hundreds of millions of light years across, containing almost nothing at all. This is the large-scale structure of the universe, and it is one of the most powerful pieces of evidence that dark matter is not merely real, but essential. The cosmic web was not predicted by observation. It was predicted by theory, specifically by computer simulations of how the universe would evolve if it began with the tiny density fluctuations observed in the cosmic microwave background, and was composed of roughly 5 parts dark matter to 1 part ordinary matter. These simulations, which trace the gravitational evolution of millions or billions of particles over cosmic time, produce a universe that looks remarkably like the one we observe. Dark matter collapses first, pulled together by gravity into filaments and halos. Ordinary matter follows, falling into the gravitational scaffolding that dark matter has already built. Galaxies form at the intersections of filaments, where dark matter density is highest. Clusters of galaxies assemble at the largest nodes, and between these structures, the voids grow emptier as matter drains away toward the gravitational wells. The agreement between simulation and observation is striking. The Millennium Simulation, one of the most famous computational efforts in cosmology, traced the evolution of 10 billion particles representing dark matter through 13 billion years of cosmic history. The result was a universe that reproduced the observed distribution of galaxies, the clustering statistics measured in large galaxy surveys, the abundance of galaxy clusters, and the sizes of cosmic voids. Later simulations such as Illustris TNG, and EAGLE added ordinary matter, gas dynamics, star formation, and feedback processes from supernovae and supermassive black holes, producing even more detailed and realistic virtual universes. In every case, dark matter was the indispensable ingredient. Simulations without dark matter failed to produce anything resembling the observed universe. The structures were wrong, the timing was wrong, the distribution was wrong. Only with dark matter did the simulated universe match reality. These simulations also revealed something about the role dark matter plays in the formation of individual galaxies. In the standard picture, galaxies do not form in isolation. They form inside dark matter halos, vast, roughly spherical concentrations of dark matter that collapse out of the expanding universe and provide the gravitational potential wells into which ordinary matter falls. The gas that will eventually become stars first accumulates at the center of a dark matter halo, cooling and condensing until it reaches densities high enough for star formation to begin. The visible galaxy that results the disk of stars, the spiral arms. The central bulge is merely the luminous core of a much larger dark matter structure. This picture explains many observed properties of galaxies that would otherwise be puzzling. It explains why galaxies of different sizes have different properties. It explains the relationship between the mass of a galaxy's central black hole and the velocity dispersion of its stars. It explains why satellite galaxies orbit their hosts in the patterns they do, and it explains the observed correlation between the luminosity of a galaxy and its rotation velocity, the Tully-Fisher relation, which emerges naturally from the physics of dark matter halos. But the picture is not perfect. On the largest scales, the scales of filaments, clusters, and voids, cold dark matter simulations match observations beautifully. On smaller scales, within individual galaxies and their immediate surroundings, some tensions remain. Early simulations predicted that every large dark matter halo should be surrounded by hundreds or thousands of smaller satellite halos, each potentially hosting a small dwarf galaxy. Yet observations of the Milky Way revealed far fewer satellite galaxies than predicted. This became known as the missing satellites problem, and it generated significant discussion about whether the cold dark matter model was correct at small scales. Over time, the tension has eased. Improved simulations that include the complex effects of ordinary matter, the energy released by supernovae, the radiation from young stars, the heating of gas by ultraviolet light, have shown that many small dark matter halos would never form visible galaxies at all. The gas within them would be heated or expelled before stars could form, leaving the halos dark and invisible. At the same time, deeper observational surveys have discovered many more faint satellite galaxies around the Milky Way than were known a decade ago, further closing the gap between prediction and observation. The missing satellites problem has not vanished entirely, but it has softened considerably, and most cosmologists regard it as a challenge of astrophysical modeling rather than a fundamental failure of the dark matter hypothesis. Another small-scale tension involves the internal structure of dark matter halos. Early simulations predicted that dark matter density should increase steeply toward the center of every halo, forming a sharp cusp. Some observations of small, dark matter-dominated galaxies, however, suggested flatter central density profiles cores rather than cusps. This became known as the cusp core problem. And like the missing satellites problem, it prompted questions about whether cold, dark matter was too simple a description. Again, more sophisticated simulations that include the effects of stellar feedback have shown that repeated episodes of gas inflow and outflow can redistribute dark matter within small galaxies, transforming cusps into cores through a purely gravitational mechanism. The dark matter itself does not need to be different. The complex interplay between dark and ordinary matter is sufficient to explain the observations. These small-scale challenges have been productive. They have driven improvements in simulation techniques, deepened understanding of galaxy formation, and motivated careful observational campaigns to measure the properties of the smallest and faintest galaxies in the universe. They have also inspired theoretical work on alternative forms of dark matter: self-interacting dark matter, warm dark matter, fuzzy dark matter that would naturally produce softer density profiles and fewer small halos. Whether any of these alternatives will prove necessary remains an open question, but their exploration has enriched the field. Not everyone, however, is convinced that dark matter exists at all. Since the 1980s, an alternative approach has proposed that the gravitational anomalies attributed to dark matter might instead be explained by modifying the laws of gravity themselves. The most well-known of these proposals is modified Newtonian dynamics, known as MOND, introduced by the physicist Mordechai Milgrom in 1983. Milgrom suggested that Newton's second law of motion, the relationship between force, mass, and acceleration, might break down at very low accelerations, precisely the regime that governs the outer regions of galaxies, where rotation curves are flat. MOND was designed specifically to reproduce flat rotation curves without invoking dark matter, and in this narrow domain, it has been remarkably successful. With a single new parameter, a critical acceleration scale below which gravity behaves differently, MOND can predict the rotation curves of a wide variety of galaxies with impressive accuracy. For some researchers, this predictive success is compelling evidence that something is wrong with our understanding of gravity rather than our inventory of matter. But MOND faces serious difficulties beyond galaxy rotation. It struggles to explain the dynamics of galaxy clusters without introducing some form of unseen matter, the very problem it was designed to avoid. It cannot naturally reproduce the acoustic peaks of the cosmic microwave background, which are beautifully explained by cold, dark matter. It offers no straightforward account of the bullet cluster, where the gravitational mass and the ordinary matter have been physically separated, and it has proven difficult to extend into a fully relativistic theory that is consistent with general relativity and the broader framework of modern physics, though attempts such as Tevis tensor vector scalar gravity have been made. The debate between dark matter and modified gravity is not merely academic. It touches on some of the deepest questions in physics: whether general relativity is the final word on gravity, whether the standard model of particle physics is complete, and whether the universe contains fundamental constituents that remain entirely unknown. Most working cosmologists favor dark matter because it explains a wider range of observations with fewer assumptions. But the MOND community has raised important questions that continue to stimulate research, and the possibility that gravity itself might behave unexpectedly at certain scales has not been definitively excluded. What both sides agree on is that something profound is missing from our understanding. Whether the answer is a new particle or a new law of nature, the universe is telling that the physics we know is incomplete. The flat rotation curves, the bending of light, the patterns in the oldest radiation, the architecture of the cosmic web, all of these observations point to the same conclusion. The visible universe is a thin luminous film stretched over a vast invisible framework. And understanding that framework is one of the great unfinished tasks of science. Perhaps the most remarkable aspect of the dark matter story is how much has been learned from something that has never been directly seen. Through its gravitational influence alone, dark matter has revealed its presence at every scale, from the smallest dwarf galaxies to the largest structures in the observable universe. It has shaped the formation of galaxies, guided the growth of cosmic structure, and left its signature in the oldest light. It has driven the construction of underground laboratories, the launch of space telescopes, and the development of some of the most powerful computer simulations ever created. It has resisted detection with a stubbornness that is either deeply frustrating or deeply, deeply beautiful, depending on your temperament. And it has reminded us, with quiet persistence, that the universe is under no obligation to be easy to understand. Tonight, as you lie still and the world grows quiet around you, consider for a moment the strangeness of where we have arrived. Nearly a century has passed since Fritz Zwicky first noticed that the galaxies in the Coma cluster were moving too fast. In the decades that followed, Vera Rubin measured the impossible rotation of spiral galaxies. Gravitational lensing revealed invisible mass bending the fabric of space-time. The cosmic microwave background encoded the signature of dark matter in the oldest light in existence. Simulations demonstrated that without dark matter, the cosmic web, the grand architecture of everything, would never have formed. And deep underground, in laboratories shielded by kilometers of rock, the most sensitive instruments ever constructed have listened for a signal that has not yet come. The evidence is overwhelming. Something is there. Something vast. Something quiet. Something that outweighs all the stars and all the gas and all the dust in every galaxy combined by a factor of 5. It shaped the universe before any star existed. It built the scaffolding upon which every galaxy you have ever seen was constructed. It surrounds you at this moment, passing through the walls, through the floor, through the air you breathe, through you. Without leaving the faintest trace, it is the most abundant form of matter in the cosmos, and it has never been touched, captured, photographed, or identified. This is not a failure of science. This is science at its most honest. The universe has presented a question so profound that answering it requires rethinking some of the deepest assumptions about what matter is, what forces govern it, and what the cosmos is made of at its most fundamental level. The question has not been ignored. It has been pursued with extraordinary creativity, discipline, and patience across nearly every branch of physics and astronomy. Thousands of careers have been devoted to it. Billions of dollars have been invested in instruments designed to catch a particle that may interact with ordinary matter only a handful of times per year in a detector the size of a small building. The commitment to answering this question is itself a remarkable statement about what human beings are willing to do in the pursuit of understanding. And the search is far from over. A new generation of experiments is taking shape. The next generation of liquid xenon detectors will be larger and more sensitive than anything that exists today, pushing into regions of parameter space where many theoretical models predict dark matter should finally become visible. New technologies are being developed to search for axions' resonant cavities, tuned to detect the faint conversion of an axion into a photon in the presence of a powerful magnetic field. The Axion Dark Matter experiment and its successors are systematically scanning frequency ranges, listening for a whisper that would confirm one of the most elegant theoretical predictions in particle physics. New telescopes are mapping the universe with unprecedented precision. The Vera C. Rubin Observatory, named in honor of the astronomer whose rotation curve measurements transformed our understanding of galaxies, will survey the entire visible sky repeatedly over a decade, cataloging billions of galaxies and measuring weak gravitational lensing with a statistical power that dwarfs all previous efforts. Its data will produce the most detailed maps of dark matter distribution ever created, tracing the invisible scaffolding of the cosmic web across billions of light years. The Euclid Space Telescope, launched by the European Space Agency, is designed to measure the shapes and distances of billions of galaxies mapping the geometry of the universe and the growth of cosmic structure with extraordinary precision. Its observations will constrain the properties of dark matter and dark energy simultaneously, testing whether the standard cosmological model continues to hold or whether new physics is required. Gravitational wave astronomy, still in its infancy, may also contribute. If primordial black holes constitute a fraction of the dark matter, their mergers would produce gravitational wave signals detectable by current and future. The ripples in space-time, first detected in 2015, have already opened a new window on the universe, and as sensitivity improves, the gravitational wave spectrum may carry information about the dark sector that electromagnetic observations cannot access. And perhaps the answer will come from a direction no one has anticipated. Science has a long history of solving its greatest puzzles through unexpected discoveries, observations made while looking for something else entirely, theoretical breakthroughs that reframed old questions in new ways, experimental anomalies that refused to disappear. Dark matter may follow this pattern. The particle or phenomenon that explains the missing mass may be something that current theory has not yet imagined, something that will seem obvious only in hindsight, the way so many great discoveries do. What is certain is that the question will not be abandoned. It cannot be. Dark matter is not a marginal curiosity or a minor discrepancy in the data. It is the dominant form of matter in the universe. Understanding it is not optional for any complete description of reality. It sits at the intersection of cosmology, particle physics, astrophysics, and gravitational theory, a single question that connects the smallest scales of nature to the largest structures in existence. Solving it will almost certainly require new physics, and new physics is the horizon toward which all of fundamental science is always reaching. There is something peaceful about sitting with a question this large. Not every mystery needs to be solved tonight. Not every answer needs to arrive on schedule. The universe has been carrying dark matter for nearly 14 billion years, and it will continue carrying it whether we understand it or not. The galaxies will continue to rotate. The cosmic web will continue to hold. The oldest light will continue to stream across the void, carrying its ancient patterns to anyone patient enough to listen. And perhaps that is the deepest lesson dark matter has to offer. The universe is vaster and stranger and more layered than anything our senses were designed to perceive. What we see, the stars, the galaxies, the nebulae, the familiar matter of our daily lives, is a thin, bright surface stretched over something immeasurably deeper. We live inside the mystery. We always have. The darkness is not empty. It is full, rich, structured, and patient, waiting quietly for the moment when our instruments and our understanding finally become sensitive enough to hear what it has been saying all along. For now, let the question rest. Let the stars continue their slow rotation overhead, held in place by forces both seen and unseen. Let the cosmic web stretch silently across the void, its dark scaffolding supporting everything that shines. Let the detectors listen in their deep underground chambers, and let the telescopes trace their careful arcs across the sky. The universe is mostly invisible, and that invisible majority has shaped everything you have ever seen. It built the galaxy you live in. It guided the formation of the star that warms your world. It created the conditions for the atoms in your body to exist. You are, in a very real sense, a product of dark matter's influence, assembled from ordinary matter that fell into a gravitational well carved by something no one has ever seen. Let that thought settle gently as the night deepens. The mystery is not frightening. It is an invitation to wonder, to search, to remain curious about a universe that has so much more to reveal. The darkness between the stars is not empty. It never was. Close your eyes. The universe will keep its secrets safe until morning.